Yeah, hi guys. Hi guys. Sorry for the last 2 days. Yeah, I didn't upload the YouTube file for grade 12 HL Math, HLAA especially. Yeah, the but anyway, yeah. I resume from today. Today's topic is mathematical induction. In mathematical induction questions, I can categorize the questions in a few different categories. The first one is sigma question. The second thing is inequality question. The third one is about the trigo questions. Trigo together with the complex. The fourth one is derivative questions. Lawfully, yeah, I can categorize into four different categories about this mathematical induction stuffs. I don't think I can cover all these four by one shot. So probably I can cover the first one and the second one today, and then the third one and fourth one by next time I think, which is tomorrow. I hope. Okay. The first sigma. The no before I go into the detail, the questions. I can just briefly introduce what is the mathematical induction rate. This is so-called the pattern proof sequence. We have pre-assigned the sequence we need to follow. Once we follow all the steps, then yeah, we have proved the statement at the very beginning of the question. Right? The first step is we need to set the statement. We better to set the statement by Pn something like that. It's easier for us to uh, write, yeah, the sentences during the proving process. The second step, we need to prove for the case of n goes to b1. In other words, we need to prove for at p1, right? The third one, assuming pk is true, and then we write what is pk. Then the next step is proof pk plus 1 is also true based on pk is true. Yeah, this is the tricky part, right? And the last one is write the conclusion. Those are the steps, yeah, we need to follow. Okay, let's go into the examples one by one. The first example can be the sigma type questions. Let me try to find the question here from the past papers. Oh yeah, we have one more example there. Divisibility. Yeah, sorry, I forget about that. Sigma type question. Where is it? Okay, here. I tried to solve 269. Oops. This is the first question. Yeah, I forget to put here one more thing. That is divisibility. And there is one more example about the divisibility as well. Anyway, the first example is this one. The using mathematical induction prove that sigma is blah blah blah. So that the first one is let we make the statement P n to be sigma r is from 1 to n r plus 1, 2 to the power of r minus 1 goes to n times 2 to the power of n for all n in the positive. So we make the statement Pn is blah blah, right? Then the next step is we need to prove P1, right? For n goes to P1. Usually for n is 1 proving, yeah, we write like this. We calculate left hand side. That is sigma r is 1 from 1 to 1 r plus 1 times 2 to the power of 1 minus 1. Right? No, r minus 1, sorry. R minus 1, which is just 1 plus 1 times 2 to the power of 1 minus 1, which is 2 times 1 is 2. Your left hand side is 2, your right hand side n is 1, so the 1 times 2 to the power of 1, which is 2. Since your left hand side goes to be the same with your right hand side, that's why you can say P1 is true. Then the next step is assuming PK is true, right? Then we better to write what is the PK here. That is sigma r is 1 to k r plus 1 times 2 to the power of k, no, sorry, r minus 1 goes to be k times 2 to the power of k. Is true. That's what we have assumed, right? Then the next step is to prove pk plus 1. In this case, what we need to go for at the end is yeah, is known to us, which is instead of k here, yeah, we need to reach the answer at the end goes to be like this, right? That's why we start from the left hand side and then we simplify and simplify and simplify it to reach up to there. That's what we need to calculate here. And then your left hand side of pk plus 1 is instead of k, instead of n, yeah, we should put k plus 1 here, right? And then r plus 1 times 2 to the power of r minus 1. After that, we calculate a lot to reach there. That's the goal to reach, right? Then we should be aware what's the meaning of k plus 1 and then k here. We are adding from 1 to 1, 2, 3, 4 up to k, right? And then this one is okay, 1, 2, 3, and then up to k plus 1, which means 1, 2, 3, blah 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 k, and then plus one more term we have. So that we split this into two. What? The first part is r is 1 to k, and then we split another one which is k plus 1. So we plug k plus 1 into r, right? So that k plus 1 plus 1 times 2 to the power of k plus 1 minus 1. So we plug here and here k plus 1 and k plus 1. We split into two, right? Then this merge is what? Now exactly the same with this one, which means we can replace this yellow box by k times 2 to the power of k, correct? So that this one is k times 2 to the power of k plus this one is k plus 2 times 2 to the power of k, right? Then we have 2 to the power of k here and there so that we can factor it, k plus 2 times 2 to the power of k. Then there is 2 times k plus 1, because this is k plus 2k plus 2, right? Times 2 to the power of k. And then this 2 and this 2k to the power of k, we can merge them together. Then k plus 1 times 2 to the power of k plus 1. Oh, this is your right hand side of k plus 1, pk plus 1. Right? That's the same with this thing. That's why we can say pk plus 1 is also true. And we have proved everything. What we need to do more is make the conclusion. So that we can start the conclusion like this. Consequently, P1 is true. And then pk plus 1 is also true whenever your pk is true. Therefore, we say that Pn is true for all the values of n which is in positive integer. Can you see all the flow of this mathematical induction? P, in order to prove the statement by mathematical induction, first we set the statement. Second, we prove for the n is 1. Usually, when we prove for n is 1, when we prove P1, we usually calculate left hand side and then right hand side separately, and then show those two are the same. That is the way for usually we do for proving P1 is true. And then the next step is, okay, PK is true, assuming the PK is true, so that we write the PK form exactly the same. Why? We will use that form for the later part, right? And then the next step is to prove PK plus 1. Yes, we need to prove for the PK plus 1. Then for this step, we usually how we do is we start from the left hand side, and then we know what is our goal, right? So that we bring the expression for the pk plus 1, and then we modify, simplify, blah blah blah, and then reach to the right hand side, our goal. During those steps, we can take what we have assumed previously, pk, right? So that you just bring the right hand side, simplified form of the pk on the on right hand side. You bring for simplify your pk plus 1. Then, because this is the proving question, always the answer is there. Okay. Then the second example is about the inequality. I'll go up. Okay. I solve for the number 259. The first one is just basic information. The reason for the reason why the question has question A and B in front of the mathematical induction question here is later part. We will use those two things. That's the purpose of A and B, right? So that, okay, let's try to prove number A first. Show that blah blah is the same with blah blah. We can start from the left hand side. Square root n plus square root of n plus 1, and 1 is there. In order to reach to the right hand side, okay, we can multiply, kind of conjugate here on the bottom and the top, right? Then by the formula of a plus b, and then a minus b goes to be a squared minus b squared, correct? So that your bottom goes to n minus n plus 1, right? Then your top side goes to be square root to n minus square root of n plus 1. Since your bottom is negative 1, the answer goes square root to n plus 1 minus square root of n, which is your right hand side. So that is proven. Number B, this is important concept. Hence, show that blah blah is smaller than in number A, what we have done is we have shown left hand side is equal to the right hand side. But in question B, your left hand side is smaller than your right hand side. You need to show inequality. It's different question. But what we can take here is, okay, square root 2 minus square 1 is same form with this. Then what is the same form of this here? That is 1 plus square root 2 and 1, right? And then this is smaller than 1 over square root 2. That's what we we can prove. So that square root 2 minus 1 is same with what? 1 over square root 2 plus square root of 1 by question A. And then this is smaller than square root 2 and 1. Right? So that we have shown it already. Your denominator was to be smaller than your entire fraction was to be bigger, right? That's the thing. Okay, then now we start from the induction question. Sigma r is from 1 to n. 1 over square root r is bigger than square root of n. For n is bigger than 2. Bigger than or equal to 2. Let's say this is just Pn, so that we don't need to write it the one more time. Then what is P1? When n goes to be 1, your left hand side is, left hand side, no, n is 2, yeah, because our starting number is 2. Your left hand side is sigma r is 1 to 2 square root r and 1, which is 1 over square root 1 plus 1 over square root of 2, and then there is square root 2 and 1 plus square root of 2, correct? Okay, good. Your right hand side is square root of 2. Which one is bigger? How do we know that? We must, okay, make your denominator the same way. Okay, this one is 2. We multiply square root 2 here and there, then square root 2 plus 2. And then if we put the square root 2, the 2 on the bottom, because we want to make your denominator to be the same, right? And your top side is 2 square root of 2. 2 square root 2 and then square root 2 plus 2. Which one is bigger? 2 and then square root 2 plus square root 2, right? So that your left hand side is bigger than your right hand side. Because 2 is bigger than your square root 2. All the rest is the same, right? So that proven. Then assuming that pk is true. What is that? Sigma r is 1 to k, square root of r 1 is bigger than square root of k. That's pk, right? Statement pk, that is true. Then to prove pk plus 1 is also true, your left hand side, it must be bigger than your right hand side at the end, right? Your left hand side goes to be, okay, as sigma r is 1 to k square root of r and 1 here. And then we split, no, k plus 1, sorry. We split the sigma into two parts, right? The first part is same with pk's left hand side, and then we have square root of k plus 1 and 1. We plug k plus 1 to there. We have done this, the same process in previous example, right? And then this one is left hand side of your pk, so that we bring the right hand side, then square root of k. Square root of k is bigger than this part, so that smaller than this part, so that, yeah, we have inequality instead of the equal sign, right? Square root of k plus 1 and 1 here. After that, yeah, we had two examples in front. What was that? The first one is square root 2 minus 1, and 1 is bigger than square root 2 and 1, right? Is it? No, 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 no. A little bit different. Square root 2 minus 1 is, yeah, this one we had previously. And then another example was, okay, square root of k plus square root of k plus 1. And 1 is the same as square root of k plus 1 minus square root of k. And then our goal to reach is square root of k plus 1 on the right hand side, right? Oh yeah, we want to have this. We don't want to have this square root of k. In this formula, we have minus k. So that if we can change this into this form, then minus square root of k plus square root of k can be disappeared, right? Then, in order to get this yellow color circle, what we need to have is this orange color, right? And then by comparing those two, which one is bigger? This one is bigger, right? So that this is bigger than square root of k is still over there. And then here we can put, is it true? True. Then the next line we can change. Then all your right hand side now reach to the square root of k plus 1. And then we have two inequality, same direction inequality in front, so that if I compare this left hand side and your right hand side is bigger than right hand side. That's why your left hand side is bigger than your right hand side. Well, I have proven this, right? That's why pk plus 1 is also true. Then consequently, blah 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 blah. Yeah, you can just copy the same sentence here. Correct? Yeah, this is the second example, inequality. Up to here, yeah, that's the same thing. Just copy of your left hand side of the pk plus 1 and then split this into two parts. The first part is the same with pk left hand side or pk, right? And then the rest. And then bring the right hand side of your pk. And then the rest simplify. Then we can reach. Of course, yeah, saying like that is very easy always. Actual calculation is more difficult. Yeah, I can understand that. No way you should do it. Okay, the last one, I will go for another example today that is divisibility. Can I do this? This is the divisibility question. Use mathematical induction to prove that blah blah is divisible by 6. pk. We need to set pk, right? Okay, n times n squared plus 5 is divisible by 9. Or, no, sorry, not 9, 6. Or multiple of 6 is the same sentence, right? Okay, when n is 1, the given number is 1 times 1 squared plus 5, which is 6, which is multiple of 6. That's why P1 is true. And then the second sentence, the next thing we should do here is assuming, right? pk is true. Oops. Which means p given number here in this case is k times k squared plus 5 is multiple of multiple of 6, so that I can rewrite this in this way. Can be 6 times of I is integer. Then we can say that there is multiple of 6, right? Then to prove pk plus 1, the given number is k plus 1 times k plus 1 squared plus 5. That's our given number, right? Then what we do is we need to bring the fact, the thing we have assumed that is true, right? There's this one, k times k squared plus 5 goes to be 6 times integer. Then what we need to do is we should make the same form of this from this line, so that we can substitute that by 6i, correct? Then how do we do in this way? K plus 1, we expand this first to k squared plus 5 and then plus 2k plus 1, right? Then together with k and k squared plus 5, yeah, we put k squared plus 5. Then all the rest goes to be like this, plus 2k squared plus k plus 1 times everything, that is k squared plus 5 plus 2k plus 1. Yeah, I put everything there. Then we simplify the rest of the things first, that is 3k squared plus k and 2k, which is 3k plus 6, right? And then instead of this part, we can bring now 6i by assumption of pk is true, right? 6i, and then those two, yeah, I can rewrite like this: 3 times k plus 1 and then plus 6, and then we can say that, okay, k plus 1 is even number, yeah, consecutive to integers, yeah, multiple of consecutive to integers is always even number, one of those two is even, correct? And then 3 times k plus 1 is multiple of 3 with even, which is multiple of 6. That's why this term is multiple of 6. And 6 is multiple of 6. 6i is also multiple of 6, right? So all the three terms are multiple of 6. And then sum of multiples of 6. I can say that here, sum of multiple of 6 is multiple of 6. That's why this is multiple of 6. So that pk plus 1 is also true. Of course, we can introduce another integer like j, so that, yeah, 3 times k plus 1 is kind of 6 times j, and then everything we can factor by 6, and then 6 times integer. That's why this is, that's the same, yeah, with those sentences. It's up to you whether you just write like this or you just switch k times k plus 1 as 2j or whatever. It's the same. Okay, so we have done everything, right? So then now you can say consequently blah blah blah. So today I have introduced three examples of the mathematical induction. At the very beginning, I said mathematical induction, there are five different categories of the questions. First one is sigma questions, and then inequality questions, and then divisibility questions, and then two more questions are there. The one is trigonometry or complex numbers, yeah, and then another one is derivative, right? So yeah, today the part one of the induction is up to here, and then maybe tomorrow, yeah, I hope I will, yeah, tomorrow there will be part two of the mathematical induction. Enjoy my, yeah, hope you can enjoy my lesson, and then good luck for you guys. Okay, up to here today. Bye.